Okay, there we go.
Okay.
Okay, there we go.
Hello, everybody. Thank you for the invitation and thank you very much for that introduction. On Mars, humans are exploring the traces of the greatest known environmental catastrophe, which is that Mars once had river networks and lakes and a habitable climate, but lost it. So on the right is one river field site, a river delta, and lake deposits. And Zhurong had a successful mission as well, shown in the top left here. I work on Curiosity rover, and the field site is shown on the right, a 5-kilometer high mountain of sedimentary rock that was suggested pre-landing to record the great drying of Mars. What Curiosity has found so far is consistent with that pre-landing suggestion. This is the most fun I've had in my career. Great geology with the bonus hope that what we learn about Mars can teach us about planets in general. So billions of years ago, Mars was habitable, much warmer than it is now. But Mars's surface today is uninhabitably cold. This is the 0th order obstacle to establishing a photosynthetic biosphere on the surface of Mars. But let's step back and look at the galaxy and the universe. When we look up at the night sky, what do we see? For thousands of years, the answer was the realm of gods and spirits. But since 400 years ago, we had a different answer. We see the night sky as a playground for surprisingly beautiful physics and chemistry. And perhaps the biggest change in the last few decades has been to add perhaps there's biology as well. Now I want to introduce another way of looking at the night sky. And this is motivated by our growing understanding of the deep geologic past of our own planet, constraints on the origin of life, constraints on how planets form, including from space telescopes and now exoplanet research. Origin of life depends on boundary conditions and parameters. If your value of such and such a parameter is too high or too low, you don't get origin of life. Planet formation and evolution also depends on parameters. If these are too high or too low, then maybe the planet forms too big or too small, or suffers a climate event that it doesn't recover from. Maybe the habitable climate doesn't persist for long. And what we've learned from the past few decades of research is that there are lots and lots of these parameters. So the alive portion of this plot is much smaller than the dead part. And ideas like this, can be worked out with lots of fancy math and the references at the bottom of this screen, but this gives the basic intuition. And so another view of the night sky is that it's entirely dead or almost entirely dead and unnecessarily so. So what do I mean by unnecessarily? Well, if being a living planet depends on lots and lots of parameters, and many worlds are just a small perturbation away from being living planets. For example, uninhabited yet habitable planets, or planets that are uninhabitable but would be habitable if things were just a little bit different. So, with that context, today I will discuss climate transitions on early Mars and in Mars's near future. So first, I'll talk about why does Mars climate evolution matter? Then I'll talk about recent developments in the early Mars climate problem. And finally, I'll discuss if humans can warm Mars in the near future. So first, the future of astrophysics in the United States is now coupled with the search for habitability beyond the solar system. There are unsolved problems in climate whose solution would be worthy of a Nobel Prize. The Nobel Prize was awarded just 18 months ago for climate research. This task or problem links many disciplines, including biology. If you're a biologist, then present-day Mars is actually not the best place to look, as its surface is sterilized by low temperatures and ultraviolet light. But if you think the origin of life requires a land surface, then early Mars becomes the best place to search for microbial fossils. So the question, what allowed lakes on early Mars, opens up a much bigger and much older question, which is our own planet, Earth, a fluke, or are habitable climates common in the universe? The concept of the carbonate silica weathering feedback, which I know is being challenged by some of you other speakers in this series, like Robert Hilton. But that concept is so useful in understanding Earth's history of continuous long-term surface habitability that when we think of the circumstellar habitable zone for planets in general, we think of it as the range of distances from the star within which this feedback might operate. So this concept guides the targeting of space telescopes like James Webb Space Telescope, shown here, and the design of their potential successors. And there are lots of planets within this theoretical habitable zone. But early Mars is outside the habitable zone. That means however much carbon dioxide you put into early Mars's atmosphere, even if you max out water vapor feedback, it's too cold for liquid water. And that's because the young sun was faint. So we know from the Mars missions, okay, so what happens if you just keep putting carbon dioxide in? It condenses as liquid on the surface. So it doesn't provide any greenhouse warming because it's not a gas, it's liquid. So we know from Mars missions that early Mars was habitable. So in the first independent test of our Earth-derived understanding of planetary habitability, that understanding has proven wrong, not once, but twice. First, Mars, that was not my intention, sorry. It's a change in the settings. First, Mars lacks extensive carbonates and tectonic cycling. It's a one-plate planet, stagnant lid, not plate tectonics. That means that the carbonate silicate weathering feedback, which relies on deep burial of carbonates to release their carbon dioxide, it probably wasn't responsible for the lake-forming climates. So that's failure. But then there's a second failure as well, which is that Mars receives such little light from the young sun that even if the carbonate silicate cycle did work somehow, then it couldn't adjust the carbon dioxide to the levels needed for surface lakes, because no amount of carbon dioxide can give surface lakes on early Mars. So this is good news. When our best theories don't match data, that means we're going to learn something. So we are basically on the hunt for a powerful non-CO2 greenhouse warming agent that can stick around for long enough to explain the geologic data. And that is the early Mars climate problem. So by studying Mars, we potentially get to study a different habitability supporting mechanism from the one that we think sustains habitability on Earth. Of course, there are other options apart from carbonate silicate weathering feedback for Earth long-term habitability, but it's still the leading candidate. And so this prospect for getting an independent test of our Earth-derived ideas is very scientifically appealing. So we need to continue searching for evidence on Earth for how the carbonate silicate feedback operates or how habitability on Earth is sustained, but with only one data point, Earth. We can't know whether the continuous operation of the weathering feedback is an artifact of survivorship bias, meaning if it didn't work, then we wouldn't be here. Mars is the only planet known to record a major habitability transition in its sediments from more habitable in the past to uninhabitable surface now. And therefore, the dynamic range of climate states available for study is much greater than we can do for any continuously habitable planet like Earth. And so even in the future, as our exoplanet telescopes get better, we will still need the long time series from geology to complement those snapshot observations over short time scales of years or decades from space telescopes. So this is the challenge. What allowed lakes on early Mars, and why did Mars dry out? And space missions continue to return tremendous data, but the basic challenge is shown right here. The present planet, the surface that the river is sitting on, is a cold desert. Nothing is moving, apart, okay, maybe the sand moves a little bit on a windy day, but there is no liquid water. But in the background, you can see this mountain that's 5 kilometers high, and that mountain is made of sedimentary rock, recording wetter conditions. And so the river is crawling up the mountain slowly, and these are some recent observations. So this press release describes clearest evidence of waves and water that NASA's Curiosity Mars rover has ever found. So the significance of this discovery is that the texture of the wave ripples, which the rover looked at very closely, indicates that they formed in a shallow lake as a result, the symmetric wave ripples as a result of wind blowing over the lake. And that means that the lake could not have had ice cover, because if the lake was ice covered, then the wind wouldn't move the sediment at the bottom of the lake. And so this is a useful climate constraint, because it says that although maybe it was cold, it was not so cold early in Mars history that the lakes had year-round ice cover on them. So this is a new discovery, which is a nice challenge to models. So why does Mars climate evolution matter? Mars is the only planet known to record a major transition in planetary habitability, and it's a window, I hope, into how planets in general behave, complementing exoplanet observations. Okay, so what are some recent developments? So Susan, Conway, and myself worked on geologic evidence for multiple climate transitions on early Mars. And so first I'd like to describe what the pictures show. The picture on the left shows rover observations, some rover observations. So in the top left, you see river delta deposits, so 4 sets exposed in cross-section, top sets prograding out into an ancient lake. In the panel marked D, you see actually Aeolian sand dune deposits exposed in the wall of an impact crater. So this records relatively dry times. However, the sand dune deposits are themselves held together by minerals precipitated from shallow groundwater. And so this environment, although a desert recorded by these ancient rocks, was much wetter than Mars is today. And in the bottom panel marked E, you see a tremendous unconformity. So at the dashed red line, we think perhaps 1 billion years of Mars history is missing. And that age estimate is based on counting craters that are partly buried, so exposed at the unconformity. So above that, you see again desert sand dune deposits, although now the sand is coming, the paleo wind direction is coming towards you. And underneath you see much older lake deposits. So there's a major climate change recorded corresponding to this unconformity. But actually 2 climate changes, because you have to have one shift to change from deposition to erosion to scour out the unconformity, and then a second change from erosion back to deposition to resume the cementation, the aqueous cementation of the sediment, but now in a desert environment. And in the background, faded because it's kilometers away, you see light tone materials corresponding to a planet-wide late event that deposited up 2 kilometers of rhythmically layered strata. These have not yet been explored by rovers. I'm very excited to see what Curiosity will find as it continues to climb. So what I'm talking about are just fragments, pieces of the puzzle that Susan and I attempted to pull together in our paper to come up with a global synthesis. So left is all orbiters. Left is all rovers. What does it look like when you look down from orbit? So on the right is an example of what you can see when you look down from orbit. So you are seeing a wind erosion into the deposit of a meandering river. And so you can see that that you are seeing several different levels within the meandering river deposit. So it's not a single stream, but you can measure the channel deposit dimensions, and you can see the point bar as it grades outwards. And so this is very useful for reconstructing paleoflow, paleohydrology. And so this you can do from orbit. And so these are the basic elements of our synthesis. But of course, there are limitations. We don't have samples. We have only 2 or 3 radiogenic dates from the rover. The Mars meteorites that we have in our collections overwhelmingly date from the dry period of Mars after the Great Drying, and so are not directly useful for this study. So here is our reconstruction. So the main point is that there are multiple cycles between wet and dry that can be correlated globally. That doesn't mean that our correlation is correct. It's consistent with the data, but to test it, we need more radiogenic dates. So within each of the wet events shown by the blue, there are many sub-events, sub-wet events, which are too small to be shown on this overall scale. When we look at the elevation pattern of the river and lakes, we see a gradual decline in where we see in the elevation of the rivers and lakes, and this we suggest can be explained as a decline in planetary temperature. So the idea being that at the high ground it becomes too cold for rivers and lakes, but low down, because of the adiabatic lapse rate, it remains warm, and therefore rivers and lakes can continue. So at the bottom, you can see mineral changes, which are that's work done by other people, mostly Bethany Ellman and Chris Edwards reconstruction. So our task, this makes our task more difficult, because not only do we have to explain the overall change, which is that we have wet conditions early on, but today we do not have wet conditions. We also have to explain these multiple shifts between wet and dry conditions. And so much of this global pattern is recorded by Mount Sharp. And so I'm very excited about Curiosity's extended mission as it climbs up through these layers. So specifically, the oldest layers at the base of Mount Sharp record the clay era. The rocks through which the rover is climbing right now record the sulfate era. And you can see in this picture, there is a change from brown to a sort of like pale white color. And that change corresponds to the switch from 4 to 6 in our reconstruction. So you may ask, well, what about 5? We think what happened at 5 is that there was so much water that it eroded the mountain and carved channels into the side of the mountain rather than being recorded by the layered deposits. So what happens when you look more closely? You see that early Mars, although it was sometimes very wet, it could not have been continuously as warm and wet as Earth is for 1 billion years of early Mars history, because if it had been as warm and wet as Earth is for 1 billion years, then we would see lots more erosion and lots more weathering. We do see some erosion and some weathering, but not that much compared to how much you would get on Earth for 1 billion years. And so that can be made more rigorous and quantitative by looking at mineral dissolution rates and sediment transport calculations. And so here we are synthesizing work mostly done by others to get those timescales. And so here is a summary figure. So these are stopwatches, and each stopwatch corresponds to the duration of the wet events during this overall time period. And the main message is that in none of these periods could Mars have been continuously warm and wet. Instead, there's intermittency, switching on and off, in and out of a habitable state. Okay, great. So now the problem is even more difficult. I will now focus for about 10 minutes on the lake-forming climates, because these are the hardest to explain. This is not the whole story of Mars history. This is just the warmest story of Mars history, and so it is the most demanding part of Mars history to explain in terms of greenhouse forcing. So can we do that? So there are, in my opinion, there are two leading hypotheses. So one is that volcanoes release hydrogen gas from underground fast enough they can build up to a mass several times that of Mars's modern atmosphere in 100,000 years or so. Why do they have to build up so quickly? Because hydrogen leaks to space. Mars has low gravity and cannot retain a hydrogen-rich atmosphere. It leaks to space, diffusion limited. So you have to do this very quickly. But if you do, then the hydrogen carbon dioxide collision-induced absorption can provide enough warming to explain the rivers and lakes. What is collision-induced opacity? So hydrogen warming by itself is not enough. Carbon dioxide warming by itself is not enough. But if you have both hydrogen and carbon dioxide in the atmosphere, then as those molecules move past each other, they will sometimes create a transient temporary 5-atom molecule, just as they are moving past each other, which can interact with infrared radiation and trap it, creating a greenhouse effect. So that's the idea behind collision-induced absorption. Okay, so another candidate is warming by water ice clouds. So we were not the first to propose this, but we are the most recent to publish on it. So I'll emphasize this possibility. This hypothesis involves only processes operating today. What you see in this picture of Mars, so this is actually a mosaic taken by a Mars orbiting spacecraft, but this is a picture, not an artist's impression, is that there are lots of water ice clouds at the low latitudes of Mars. And up at the pole, there is exposed water ice. But the clouds are not found near the pole with the exposed water ice. Instead, they are found near the equator at high altitude. Now, on modern Mars, these water ice clouds do not provide strong warming, but this process is active today. And so we wondered how intense the warming could be from water ice clouds in the past. So to test this hypothesis, we used a 3D global climate model. So we used an ice cap water source whose location we varied. Just as for modern Mars, clouds can be found far from the water source, so the clouds don't have to be on top of the water source. The ice particle radius depends on early Mars dust abundance because the dust acts as the ice nuclei for so ice particle radius on early Mars depends on details of the dust cycle, which we don't know. So we leave ice particle radius as a free parameter and see how the amplitude of our warming depends on that control parameter. Our cloud microphysics includes set laying of individual cloud particles, plus a parameterization for clumping and snowfall. So we found that a cloud greenhouse can warm a Mars-like planet to a global average annual mean temperature 265 Kelvin. So that's still cold, but that is warm enough to explain the melting and lakes, because you can have a warm season. So even if the annual average temperature is below freezing. So this is and it stays warm for centuries or longer. So I say centuries or longer because that's as long as we ran the model, and it stayed stable. So it will probably stay stable for much longer than that. This is the steady state outcome from a cold, dry start. And the X's here correspond to stable surface snow and ice. The black contour lines are topography. So shown here are all of the rover sites. So this is Zhurong rover location. So T for Tianwen. C is for Curiosity. P is for Perseverance. And R is actually a mission that hasn't launched yet. It's the European Space Agency planned mission called Rosalind Franklin rover, which will hopefully launch in a few years. IGCM, okay, so all right, so everything within the green, which is most of the planet, has a warm season that would allow melting. So as with previous 1D models, we find that we only see maps like this if we run with 10 micron cloud particle size or 20 micron cloud particle size. If we run with 5 micron particle size, they're the wrong size to efficiently absorb the upwelling infrared radiation. And so if we run with 5 micron particle size, we do not get a warm climate. So that obviously begs the question, well, what is the cloud particle size on modern Mars? And on modern Mars, the cloud particle size is very variable. It's up to 70 microns near the poles, but it can be, a few microns at the equator. And so for early Mars, we don't know the ice nuclei. So the range of cloud particle size at which we get the strong warming is within the range of modern observations, but we don't actually know if that's the cloud particle size in early Mars. Okay, so here is a cross section through the cloud structure. So now it's elevation versus latitude, and the blueness is how much cloud ice you have. So the clouds are high up. The cloud water ice mixing ratio is the blue tones. The temperature is in green contours, that's in Kelvin. So you can see these are cold clouds. And the relative humidity is in red contours. So you can see that the surface relative humidity is small. What is going on here is that, these clouds have optical depth of 1 or more, but they're physically tenuous, so a few tens of perceptible microns. So what's going on is this is time averaged, but if and also longitudinally averaged, but at some times and at some longitudes, the relative humidity at the surface is sufficiently high that cloud substance can fall down and reach the surface, and that's happening mostly at the poles. At the equator, however, as the cloud particles settle out, they fall into low humidity regions and they resublime, and so they turn into water vapor. They don't reach the surface as precipitation. This doesn't look like Earth's cloud structure at all. So what is going on? So cloud cover is near global in the GCM. This is because the residence time of water substance in the atmosphere is more than 1 year, which is 2 orders of magnitude longer than on the Earth. So this long residence time assures a low-level water mixing ratio that is uniform. So atmospheric water substance has a residence time that is longer than the atmospheric mixing time. So except at surface cold traps, individual cloud particles do not fall to the surface. Instead, they resublime just below the cloud base and they moisten the subcloud layer. And atmospheric water has no sink except for the spatially restricted cold traps, mostly at the South Pole. So for these reasons, the well-mixed water vapor bearing layer extends to high altitude where it condenses as a global capping cloud layer. So this basic behavior has been suggested previously for modern Venus and for Titan, Saturn's moon. And in the early Mars model, this cloud cap provides strong greenhouse warming. So this analysis explains why previously some researchers did see strong cloud warming in their GCM and some did not. It's the key is cloud particle size and what happens to your cloud particles, whether they fall straight to the surface unrealistically or more realistically if they resublime. So this scenario is attractive because cloud aerosol warming requires less mass to get warming, 4 orders of magnitude less mass. So for water ice clouds, we need about 5 gigatons. That's similar to polar hood clouds on modern Mars. You just distributed it differently. By contrast, building up the needed amounts of hydrogen on early Mars to explain the warming, it's physically possible. There are enough atoms to do it, but you need to erupt about 100 million cubic kilometers of magma in 100,000 years. And again, that's because hydrogen can be quite rapidly lost by escape to space. So we find warm climates when cloud particle radius is fixed at 10 microns or higher. But for early Mars, we don't know that the conditions for 10 microns were ever achieved. So this remains a hypothesis to be tested. But it is consistent with geologic data, which suggests that Mars had a warm and arid climate. In arid climates, lakes can be fed by groundwater flow, by groundwater upwelling, or transiently by melting of pre-existing ice following a cold to warm transition. In our model, the switch from cold to warm state is very fast, like 10 years. So the basic idea is that you can have a cycle where groundwater trickles in, and this is similar actually to some models of how hydrology in Western China works, where you have mountains close to the desert and springs. Water trickles in at high ground and upwells at low ground with long flow paths. More work is needed to test these proposed mechanisms, but this supports the cloud greenhouse hypothesis. In a more recent paper, we said, okay, what is the explanation for the shifting patterns of rivers in Mars history? So today on Mars, no rivers form. Very early in Mars history, rivers form over a wide band shown in the top panel. But later in Mars history, rivers become more patchy, but they also shift location. Specifically, they shift location to lower elevation, as shown in the bottom panel. What you are seeing here is a data model comparison. So we ran a large grid of GCMs varying parameters to find what was the best fit to the distribution of early rivers, and then separately, what was the best fit to the distribution of late rivers. The best fit to the distribution of early rivers was a very strong greenhouse effect to allow for melting even at high elevation. So many of these rivers are at high elevation. But the best fit later in Mars history was for a weak greenhouse effect to explain why those high elevation rivers shut down. And so we were not the first to take this basic approach for thinking about early Mars, but we were the first to do it for different periods of Mars history. So here is a summary cartoon result. Early in Mars history, we have warm and wet conditions. And later in Mars history, the temperature drops by about 10 Kelvin in order to explain rivers at intermediate elevation. So this sounds like a very simple story. It is a simple story. But remember, the warm and wet, the river forming climates are switching on and off all the time. So it's not like a monotonic decline. It's more the little bursts of wet conditions at different times, and the sort of like upper envelope of the wettest conditions, that's what's decreasing over time to explain the data. I think the aspect of the next 5 to 10 years of Mars exploration that excites me the most is decreasing costs of transport to Mars. So what you are seeing is a picture from the SpaceX Starship test flight, I think 5 weeks ago. And Starship has a payload to Mars surface of approximately 100 tons. That it's designed for a payload to Mars surface of 100 tons. But it will probably cost less than or comparable to our existing spacecraft, which take 1 ton to the Mars surface for landing. So this is a 100-fold decrease in cost per ton to Mars surface. And so this creates an explosion of possibilities. People could send bigger rovers. People could send aircraft. So a helicopter was flown on Mars. But that's not the maximum size for a helicopter on Mars. You could have a bigger helicopter that goes further. And there are many other possibilities. This is, I think, the most exciting thing for the next 5 or 10 years. So in summary, for this section, a cloud greenhouse can explain warm early Mars. Changing spatial distribution of water flow on Mars can be simply explained by about 10 Kelvin of global cooling. Although I didn't emphasize this, that cooling is probably driven mostly by loss of non-carbon dioxide radiative forcing and not changes in carbon dioxide radiative forcing. So in the final third of my talk, I would like to talk about how can we warm Mars. The artisan approach, so this would be near future humans by choice warming Mars. So the artist's impression on the left shows stages in warming Mars. And the idea is that warming Mars is a bit like descending a mountain on Earth. The current state of Mars, shown by panel A, is too cold for life. But as Mars warms, we descend the mountain, and the environment first allows cyanobacteria to live, then the environment allows lichens to live, and so on. Now, this does not get to an atmosphere that humans can breathe. That would require a second stage, in which photosynthesis raises the oxygen level. But today I'm only going to talk about the first stage, warming Mars to enable a photosynthetic biosphere, like shown here. So, can humans warm Mars enough to melt the ice in less than 30 years with current technology or technology that will be available in less than 10 years? So currently the cost of shipping to Mars's surface is about $1 billion per ton. 9 days ago, I'm sorry, not 9 days ago, less than 3 weeks ago, SpaceX released their plan for Mars. The plan says that they will send 250,000 tons to Mars every 26 months. So Mars opportunity is every 26 months. And SpaceX has almost finished building a factory shown here, whose purpose is to build 150 Starships every year. So that's one Saturn V class rocket every 2 days. What makes this plan impossible to dismiss is that the test program is successful so far. It's the most powerful launch vehicle ever by a factor of 2. It's the first launch vehicle designed for full reusability that has reached orbit. Now, SpaceX is a private company. They don't have to reveal their costs, but the costs have been independently estimated by outside researchers as $90 million per rocket and $10 million per launch. So that actually reduces the cost of shipping to Mars's surface by about 3 orders of magnitude, so even more than I mentioned previously, assuming that they get the reusability to work. Okay. So the modern discussion of warming Mars was started by Carl Sagan, and there have been, many ideas from many different countries. Here's a way of summarizing them. The main energy flux is in the Mars climate system. So this is Mars today, too cold for life. So Mars responds quickly to changes in these fluxes. So only 1% of sunlight energy can warm Mars by 35 Kelvin in a decade. Low thermal inertia from a climate perspective. Thin atmosphere, no ocean, low thermal inertia. So both the current and the warm climate, the net surface energy balance top equation is 0. So we can think of the warm climate as being a succession of steady states because the thermal inertia of the system is low. So what is that steady state in the current climate? Well, net, we have about 125 watts per meter squared absorbed by the surface. That's the incoming sunlight, 130. Subtract the reflected sunlight, 30. Add the greenhouse warming, 25, gives you 125. So from black body sigma T to the 4, that gives you about 210 Kelvin. So to get Mars warm enough to melt the ice, we need to double that 125 watts per meter squared absorbed. So we can see immediately just from this diagram that decreasing surface reflectivity won't be enough, at least not directly. That's because it buys only about 30 watts per meter squared. So either we need to supply more sunlight or stronger greenhouse effect. So are the raw ingredients for a warmed habitat available? Yes. Mars has polar caps that are mostly water ice, and if they melt, that's enough water for a 35-meter global layer if spread out evenly. In addition, 1/3 of Mars's surface has shallow buried water ice. We know this from a bunch of indirect means, like neutron spectroscopy and gamma ray spectroscopy, but also most spectacularly from recent impact craters like this one, which just splash up the buried ice onto the surface so that we can see it. So that's the bluish clumps that you can see in this picture here. And in addition, although I won't emphasize it, the nitrate content of Mars soil is actually higher than fertile soils on Earth, but the Mars soil is very salty from an Earth perspective, and the high saltiness could be a problem for future human efforts. And so, so one of those salts is perchlorate salt, which can be bioremediated by perchlorate reducing bacteria. But even though in the remainder of this talk, I'm just going to be talking about warming, there are other problems as well. And so warming is a necessary step, but not sufficient by itself. Okay, so instead of gases, how about using aerosols to warm Mars? So this study was a collaboration with my group at UChicago and Huma Maseni's group at Northwestern, with a contribution from Ramses Ramirez at University of Central Florida. We started out by investigating half wavelength metal dipoles. So we did finite difference time domain calculations of the scattering, absorption, and phase function of these particles, orientation average, because Brownian motion will tumble them. And then we put those orientation average spectra into a bunch of climate models as a new aerosol. So similar to the natural dust of Mars, such particles will be swept high into Mars's atmosphere. Remember from the clouds part of the talk, where having high clouds was important for warming? It's the same here. Having the particles stirred up high gives a stronger greenhouse effect. And we found that aluminum nanorods warm Mars more than 5,000 times as effectively as the best gases on a warming per unit mass basis. The effective particle lifetime is many years. They do eventually settle out, but they take a long time to do so because they have a much slower settling speed than natural dust. And for a particle lifetime of 10 years, the climate models indicate that release at between 10 and 30, depending on material, liters per second would globally warm Mars by more than 30 Kelvin and start to melt the ice. Now, there is a challenge with this concept, which is dispersal from a single point. So if you just release all the particles from a single point, the particles might clump and fall back down again instead of going up into the atmosphere. And so you might have to have some more spatially extended sprinkler system instead of a single release vent in order to get good dispersal. So here are some of our 3D results. So the main point is that you need a couple of 100 milligrams per square meter, which is still a lot of mass, to warm Mars. Here are some of our 3D model. So we in the model, we try different engineered aerosol loadings and see what the climate would be. So I'm showing you an intermediate one where the planet is warm enough for melting, but only just. And so you can see that the melting occurs first in the southern ice belt. And the reason for that is that Mars's orbit is eccentric, and that its current orbital configuration, meaning the current phase of Mars's Milankovitch cycles, Mars's south pole points at the sun during southern when Mars comes closest to the sun, and so that means you get a very warm southern summer. Okay, so if the lifetime is 10 years, which is reasonable, then the flow of aerosol that you need is 12 liters per second. That is one garden hose is 1 liter per second. So this is 12 garden hoses to warm Mars. There are many questions that this opens up. So one is thinking more carefully about climate feedback. So Mars has natural dust cycle, natural water cycle as well. And both those cycles will get more intense as the planet warms. And some feedbacks will be positive, meaning they will accelerate the warming. For example, water vapor feedback will accelerate the warming. On the other hand, some feedbacks will probably be negative. If more dust is stirred into the atmosphere as the planet gets warm, the dust will reflect sunlight and will tend to cool the planet relative to what you would get with no dust. And so thinking about all these feedbacks in the context of realistic aerosol transport, nucleation, and so forth is important. And second is, we don't think we're anywhere close to finding the best particle. Basically, what I have shown you today and what is described in our manuscript is the first particle we tried, because the computations are quite computation expensive. So there are many other possibilities. For example, graphene nanodiscs is something that we're currently excited about, which could provide further increases in warming efficiency and therefore further decreases in how much mass you need to put into the atmosphere to keep the climate warm. But sticking for a moment with the aluminum option, its abundance in the Mars soil and the quantities are not large by like Earth mine standards, and so a relatively simple soil scraping system could provide enough metal to keep the fountains running at 12 liters per second. Okay, but so far I've just talked about it like it's obviously a good thing, but we don't know that it's obviously a good thing. There are many factors that have to be considered. If a photosynthetic biosphere can be established on the surface of Mars, perhaps involving synthetic biology, that might increase the solar system's capacity for human flourishing. But if Mars already has life, then study of that life could have great benefits that justify robust protections for its habitat. And we don't actually know how much this would cost in money and effort. And so further research into particle design and manufacture, including climate modeling, could reduce the cost of this method. I think key experiments that will be needed include Mars pressure wind tunnel experiments for what these particles do when they reach the surface. Do they get stuck forever, or like natural dust, are they lifted up again by the wind? That affects the effective particle lifetime. More detailed simulations of exactly what is happening at the release point. How concentrated can the release be without causing undesired clumping of the particles, say. Also, today I have only talked about the method that we have worked on, but there are other methods as well. For example, Robin Wordsworth's group at Harvard has suggested a local warming method where you put silica aerogel out onto the surface of the soil, which lets sunlight in but traps infrared, creating a local warm soil area. And because what the elegant aspect of this method is that because of the low thermal conductivity of the silica aerogel, the heat is trapped. And so the atmosphere can stay cold, but the surface is warm. So certainly any serious investigation of this idea would have to consider other approaches such as this local method. Okay, but yeah, I mean, this would not get all the way to an atmosphere that humans could breathe. It would just be a first step to establish a photosynthetic biosphere. And just as on our planet, oxygen production by photosynthesis would then alter the oxygen concentration of the atmosphere. Okay, so that's it. I'll just leave out my main conclusions, and I'd be happy to take any questions. Thank you.
Great, thank you very much, Edwin. That's the time for questions from our participants. So feel free to open your mic to ask a question, or you can leave the question in the chat box, and then I could read the question on behalf. So yeah, go ahead. Okay, let me start the question. Okay, I know that for the aerosol to keep the to have the greenhouse effect, is that also one possibility for Earth's early, let's say, greenhouse effect that it could deal with a Yang-Sun paradox?
Maybe, but I'm more familiar with aerosol as a cooling agent. So hypothesis is that hydrocarbon haze cooled early Earth. And so the idea is that if the methane that is produced by life on early Earth, if the methane concentration gets too high prior to the great oxygenation event, then hypothesis is that forms hydrocarbon haze, which reflects sunlight back to space and cools the planet. So this was suggested in the late 2000s as a self-regulation mechanism. Why self-regulation mechanism? Well, the temperature preference of methane-producing microbes could mean that when things are cooled down by the haze, then the methane-producing microbes slow down their methane production. But this is speculative. We have no proof that this happened on early Earth. Some people have looked for that signature, both isotopic signature of haze and also just, haze deposits, but to my knowledge, none have been found. Do you know of any such deposits?
No, I don't know. Because yeah, I was just curious about the Yang-Sun paradox to solve that on Earth. So yeah, and I saw your talk that mentioned about aerosol
Yeah.
impacts on that. Yeah.
A planet, so a world on which aerosols, aerosols matter a lot for the climate of Venus, Earth, Mars, and Titan today. But perhaps the most fun is Titan because methane is a greenhouse gas, of course. But methane on Titan also produces haze, and the haze tends to cool Titan. And so it's an interesting balance between those two factors. Yeah.
Okay. Another quick question: that for Mars, that do we have we detected the for example, organic compounds on the surface such as enzyme? Yeah, because we know that in Haidian, for example, the Earth must have this enzyme already. For example, according to the like carbon isotopic ratios and measure in those Geological of the graphite capture as a mineral inclusion in Geological zircons. So those should be having the symbol of the fractionation that caused by the enzymes, for example. So I don't know that when on Mars that have people already detected those organic compounds, especially in the earlier part of the Mars. I'm curious about.
So we do not have any evidence that life has ever existed on Mars. So organic compounds have been detected. However, they have many possible origins. Just as in meteorites, there is percent level organics, but no one thinks that the meteorites have life. In terms of the so the organic concentration is hundreds of parts per million by weight. the organic composition is poorly constrained. So yes, there's a lots of benzene rings, and there's a lots of aromatics. Many of them have sulfur on them. The isotopic data is hard to interpret. So the isotopes cover a wide range, and the isotopic data for carbon, as measured by Curiosity, is hard to interpret because so many processes could have affected it, and because it is so extreme relative to Earth. So if you're interested in the organic carbon isotopes, then I recommend Christopher House's paper in PNAS. And if you're interested in the carbon isotope data for inorganic carbon, then I recommend Heather Franz, Franz, Nature Astronomy paper. They are good, data description papers, but they include a hypothesis section, and there are lots of hypotheses that could explain the data. Yes, life is one option, but there are lots of other options.
Okay, thank you. Okay, questions for other participants? Yeah. Please go ahead.
Yeah. Hello, Edwin, Kite. This is Jatin Liu from. Hello. Nice to meet you. Yeah. This is Jatin Liu from the University of Hong Kong, and
yes.
a very nice talk. Thank you very much. And my question is: you propose a great aridity on early Mars around 3.5 billion years ago, and what caused the great aridity? And what's the reason for the great aridity? Thank you very much.
Good to see you. I really like your papers.
Thank you very much.
So one way to think about the aridity is why does Earth have relative humidity that is quite high on average? And that's because we have a big ocean. But if Mars had a small ocean or no ocean at all, then so for example, water ice. So this is the output from the climate model, and you can see there is great aridity in the low latitudes. This contour is 0.25 relative humidity, which is like a very dry desert by Earth standards, and it's a very dry desert all the way from -40 to +40. Okay, so why is the climate model producing this? The climate model is producing this because the poles, which is where the water ice is, the poles are much colder than the equator. And so, so it's a cold trap situation. Now, of course, that means that we need the water to be coming from groundwater upwelling in order to explain why there are lakes near the equator if the if there is no ocean at the equator. Did that address your question?
You mean the water go to the polar regions, right?
Yes.
This causes the aridity in the equatorial region. And I'm also wondering the great aridity around 3.5 billion years old. Yeah, in your 6 or 5, this one, 3.5, the episode 3 to 4, So, so it's very arid in your model, right?
Yeah. So yes, go ahead.
So what's the evidence for the great aridity?
Yes, primarily wind erosion surfaces. So in many places on Mars, we see that early formed materials were eroded by wind at around this time. So can you have wind erosion under wet conditions? It's difficult. So wind erosion is carried out by sandblasting. And if the sand is hopping along, but there is a lake, then the sand will fall into the water. And now I don't have any clasts or tools to carry out the wind erosion. So we do not observe aridity directly. What we observe is wind erosion surfaces. And from the wind erosion surfaces, we infer aridity. to the first part of your question, which is why should this happen? We don't know, but we suspect, or like one candidate is orbital change. So just as for the Earth, Mars undergoes Milankovitch cycles, but unlike the Earth, Mars undergoes chaotic, large amplitude jumps in mean obliquity. So Mars will be wobbling like this, and then Mars will start wobbling like this. And everyone agrees that such an event would cause a big redistribution of water and a big change in climate. So that's one candidate, but there are others.
Yeah, okay, good. So the polar wandering is important. Yeah. Okay, good. Yeah, thank you very much. Hope to see you in person soon.
Yes.
Yeah, thank you.
Yeah, good to see you.
Good. Bye-bye.
Next question, please.
Hi, Professor Kite. I have a question. I don't know if you remember me. I am Edwin, and I'm a PhD student, work with Steve Yang Liu, and now I am in France. I work with Nicolas Mangold.
Cool. Awesome.
And yeah, and could you I actually I want to ask the question about this PowerPoint, because you mentioned for the curiosity the next slide for the curiosity image type. I didn't really follow why does it mean the transition from 4 to 5?
So within this image, there are there's one really big unconformity. From this view, you can't see that it is an unconformity, but from orbit, we're sure it's an unconformity because we see impact craters poking out at the unconformity surface, so we can map the unconformity. That unconformity separates the sort of creamy colored, pale white color up from the dark brown rough material below. So these two units, which are called the laterally continuous sulfate orbital facies and the rhythmite orbital facies, they can be mapped out across the planet. And a postdoc working with me, Maddie Turner, is in fact doing this right now. And so the basic idea is that the unconformity, which is an angular unconformity with really deep scour, corresponds to dry conditions. So basically, 3 is a time of from 4 to 6, basically. Yeah. So if I said 4 to 5, then I misspoke. So 5 is something that is not really visible here, but it is recorded in Matchup.
Yeah, okay. Yeah, I think you meant 4 to 6. I made a mistake. And does that mean in that sketch, every column here, that means the minimum time period for a short period of warming condition?
No, our constraints for the short periods of warming are shown here. You can see that the upper limit is 1 million years. On this scale, 1 million years would be too thin to see. Therefore, for visualization, we drew them more thick than are in fact allowed by the data.
Okay.
Yeah.
Yes, okay, I understand. Thank you.
Okay. Next question, please.
It looks like there are some questions in chat. Should I open that?
Okay, there's one. Why could I not see the chat? But anyway, yeah, that would be good. Okay, so Okay, let's read the question. Considering that Mars has a more contrasting landscape, weaker gravity field than Earth, and also different precipitation from the Earth, I wonder how big difference of the erosion rate could be between Earth and Mars. Yeah.
So
yeah, that's the first question. Yeah, erosion different. The erosion rate different between Earth and Mars.
Yeah, so there are two aspects. One is transport of loose sediment, and the other is erosion of bedrock, intact bedrock. So for transport of loose sediment, there have actually been experiments in aircraft doing parabolic flights. And so we understand how the sediment transport changes at low gravity. And the corrections are relatively small. So we do have, so we expect that our equations for sediment transport that have been developed on Earth should work on Mars with well understood corrections. And the corrections turn out to be relatively small, actually. Okay. But for the second part, bedrock erosion, there, unfortunately, we do not have a good theory even for Earth. So there are many reasons for this, but one can be understood as, obviously, for bedrock erosion, it matters whether once you have fractured the rock, can you pull a slab of the rock out of its fractured container to move it downstream. And that will obviously depend on how many fractures there are. If the rock is densely fractured, the fragments that you pull out will be smaller and more easy to transport. But we don't have a theory for the fracture spacing of rock. So on Earth, we do not have a good theory for bedrock erosion, and that means on Mars we don't either. So I guess, yeah, that's my answer. Should I answer the second question or take a different person question?
Okay, how about answer the second question? So how long does this aerosol to decompose from the habitability of a human being?
As quickly as you like. So by that I mean these will be made by people, so they can be made to decompose quickly. So for example, consider the aluminum possibility. Aluminum does oxidize in air, and so if you make a small particle, it will disintegrate more quickly, and if you make a big particle, it will disintegrate more slowly. So the particles that I showed you in my talk were designed for radiative efficiency, and so they would actually decompose slowly. But you could get a similar radiative boost from a thinner particle that would decompose more quickly. What do I mean by decompose? Turn into extremely fine particles of aluminum oxide. Yeah.
Okay, any more questions? Okay, I think we have already ran an hour and kept Edwin for pretty late in Chicago. Okay, thank you very much, Edwin. Thank you again for your talk. And I think before we adjourn, could you stop sharing your screen, Edwin? So everyone, could you open your video and show your appreciation to our speaker today? And then I will turn the meeting room off in about 1 minute or less. So everyone, if you can, if it's convenient for you, please open your video. So let's do that briefly. And anyway, I think if you stop sharing screen, then you could see the faces of people. Thanks. Yeah, let's stop recording.